Good morning and thank you for your interest in my talk. I'm excited to present my recent efforts laying the groundwork for developing a smart generation of prosthetic heart valves. To give you the bottom line upfront, we present an in silico proof of concept analysis of a novel modality for remote continuous monitoring of transcatheter aortic valve or TAVs using pressure microsensors with the goal of proactive early detection of valve malfunction. Our vision is to embed pressure sensors strategically on the stent such that their measurements can be used to predict individual leaflet health. To achieve this, we employed computational models and generated a dataset of 28 high-fidelity simulations of flow-through healthy and dysfunctional valves. From these simulations, we extract pressure measurements at key locations in the valve vicinity and create hemodynamic signatures of healthy and dysfunctional leaflets. Next, we train supervised learning algorithms to answer the following two questions. Can these signatures detect reduced leaflet motion or RLM? And if so, can we quantify the amount of dysfunction? The answer to both questions is yes. On this slide, I will briefly describe how we envision such a technology to work. Patients with failing aortic valves will receive a sensorized TAV. When one or more leaflets in such a TAV experience reduced leaflet motion, it will alter hemodynamic pressure in the valve vicinity. Pressure signals can be periodically transmitted by the embedded sensors to an external internet-enabled device. Here, the hemodynamic changes will be interpreted and a prediction of valve health be made. The external device reports these changes to the patient's assigned cardiologist, who can then initiate appropriate diagnostic and therapeutic action. Our work is motivated by the increasing popularity of TAVR due to its minimally invasive nature, non-inferior patient outcomes compared to surgical replacement, and its availability to a broad range of patients. However, the bioprosthetic valves employed in TAVR are susceptible to acute and chronic leaflet thrombosis, which restrict leaflet motion. In early stages, leaflet thrombosis may be asymptomatic but may progress to clinical valve thrombosis or cause fatal thromboembolic events like strokes or heart attacks. Subclinical leaflet thrombosis in particular is detected incidentally during post-implant follow-ups, and common imaging modalities such as transesophageal echo or 4D multi-detector CT are either invasive or expose the patient to radiation and therefore cannot be used routinely. This informs a critical need for a non-invasive, non-toxic monitoring modality for transcatheter valves, which is what we want to address. In silico models are of particular value to developing such a technology since one can generate a large data set of biomechanical responses from valves with healthy and reduced mobility leaflets and precisely control the amount of dysfunction exhibited in each case. Our computational model consists of a canonical aorta and a simplified aortic valve. The aorta consists of the left ventricular outflow tract, aortic annulus, root, and the proximal ascending aorta. The aortic valve is made of three leaflets modeled as zero-thickness membranes. We integrate the 3D Navier-Stokes equations inside the aorta to obtain transient flow fields. Aortic valve dynamics are governed by a simple equation which includes the driving hemodynamic pressure and the restoring force due to leaflet elasticity. The aortic valve model is parameterized using two constants relating to leaflet inertia and stiffness. Aortic stenosis is induced by increasing leaflet stiffness over its baseline value, and leaflet mode shapes can be controlled by tuning a shape function to mimic observed leaflet motion from in vitro experiments. Finally, the fluid and structural subsystems are coupled using a sharp interface immerse boundary method. Flow is driven through the aorta using an analytic flow profile based on physiological flow measurements. The aorta lumen is discretized using a Cartesian grid with approximately 5 million grid points and a peak resolution of 0.3 millimeters. Of the 28 simulations, I will use hemodynamic differences between three baseline cases to motivate data-driven analysis. In the first healthy case, all leaflets experience normal range of motion. The other two RLM cases have valves with one or two leaflets exhibiting reduced mobility. The time-varying projected valve open area for each case is illustrated in the bottom plot and is overlaid on the American Heart Association's guidelines for determining aortic stenosis severity. The two RLM cases result in very mild aortic stenosis, so less than 20%, which is critical for early detection of RLM. On this slide, I will describe the qualitative differences in flow fields between the three cases. On the left, we have an animation showing the instantaneous systolic phase, and the corresponding animations of axial velocity and valve configurations are shown to the right. The healthy valve results in axisymmetric post-valvular flow, whereas the RLM cases show a tilting of the aortic jet away from the stiffer leaflets. This jet tilting results in impinging flow on the aorta wall downstream from the healthy leaflets and recirculating flow towards the opposite side of the aorta wall. This is also observed in systolic average axial velocity contours in transverse post-valvular planes, where red and blue contours represent antegrade and retrograde flows respectively. We can see that the healthy case shows mostly antegrade flow, while the two RLM cases show significant regions of retrograde flow downstream from RLM leaflets indicated with asterisks. These differences in flow fields are expected to result in different loading patterns on the aorta wall. Next, we look at a comparison between the pressure loading on the aorta wall in the three cases. In these plots, we have rolled out views of the aorta surface so that the azimuthal coordinate is along x and axial coordinate along y. The RMS surface pressure fluctuation is calculated as shown in the equation. The healthy case shows a circular symmetric PRMS distribution, whereas the aorta experiences stronger PRMS fluctuations downstream from RLM leaflets. This indicates that a change in leaflet status from healthy to RLM results in changes in the intensity and symmetry of PRMS distribution experienced immediately downstream from the valve. The strong coupling between leaflet function and downstream hemodynamics leads us to our central hypothesis, which states that if we can measure pressure in this region sensitive to changes in leaflet mobility, we can use supervised learning algorithms to solve the inverse problem and predict individual leaflet mobility. We propose a sensor array consisting of 6 sensors, 2 per leaflet. Of these two, one is placed in the cusp of the sinus and the other is placed downstream near the aorta. Each sensor pair is aligned azimuthally with the center line of the leaflet it monitors. The difference between the sinus and aorta pressure is tracked over systole for all leaflets from the dataset. Next, for classification, we center each measurement about the ensemble average and normalize it to unit magnitude, giving us signals like these shown in the right figure, where blue signals correspond to healthy leaflets and red signals correspond to RLM leaflets. Next, we create a data matrix from all such signals in the development set and compute a feature vector consisting of its principal components. By truncating the feature vector to the first k entries, we obtain a lower dimensional representation of our dataset. The parameter k is the primary model variable and is tuned via cross-validation. For the sake of illustration, the first 2 entries of the feature vector for the 9 leaflets from the 3 simulations described earlier are shown in this figure. We see this simple projection can help create meaningful segregation between leaflet classes such that all healthy leaflets marked by blue circles cluster together and all RLM leaflets marked using red circles form a different group. To test whether meaningful detection of RLM can be achieved using such transformation for a larger sample of leaflets, I divide the entire dataset into development and testing sets following a 75-25 split. In each dataset, various leaflet kinematics, range of motion, and inflow conditions were modeled to fill out the parameter space as much as possible and to increase the robustness of the machine learning algorithms. Then, returning to the 2 tasks for the machine learning algorithms, I used the development set to train a linear discriminant classifier and a logistic regression model. Using these, we correlate the sensor measurements to leaflet status and range of motion, and for each task, model complexity is controlled by the number of PCA modes k used for training the respective model. The optimal value of K is determined, as stated before, via cross-validation, using 54 of the 63 leaflets from the development set for training and the remaining 9 for validation. Once the optimal number of PCA modes are determined, we assess the performance of the tuned models on the test set. For classification, I show histograms of the LDA projections of the leaflets from each data set and a discrimination threshold using projections from the development set using a black dashed line. We see all projections from the healthy leaflets of the development set mapped to the left of the threshold and those from the RLM leaflets mapped to its right. More importantly, all but 2 leaflets from the test set are accurately classified into their respective categories. Likewise, a strong correlation can be established between the sensor measurements and leaflet range of motion using logistic regression. And this correlation holds well on the test set too, as demonstrated by the R-squared values on the test set. From these two results, I conclude that using discrete pressure measurements in the vicinity of TAVs, retrospective as well as prospective detection of and quantification of RLM is possible. Looking forward, we want to extend this analysis to CT scan enabled physiologically accurate aorta morphologies to account for important anatomic features such as non-circular aortic annulus and curvature of the ascending aorta. To this end, we are gathering imaging data from a small patient cohort and adapting a simplified valve model to patient-specific aortic annuli, and then generating healthy and stenotic valve flow simulations from them. With that, I would like to conclude my talk, and I'm happy to take any questions from you. Thank you.